All right, so last week we introduced the basic concept of linear block code, and we talked about the encoding procedure of LBC. And for linear block code, basically it contains two matrices. One is called the generation matrix G, and the other one is the parity check matrix H. Okay, so for G and H, by using G, we can perform encoding. So basically, we can use the information vector, which is X multiplies the generation matrix G, then we can get the code word. And the dimension of G is K by N, such that for K bits of information, they are mapped to N bits of code word. And the general structure of a generation matrix is it can be written as two block matrices side by side. We have a K by K identity matrix, and then we have a K by N minus K parity matrix. So if the generation matrix is written in this form, then the first K bits of the code word are always exactly the same as the information bits. And this is called a systematic code. Okay? A systematic code. And as I mentioned last week, so for any non-systematic code, we can always find a systematic counterpart such that their performance are exactly the same. So for this reason, we always design the linear block code as a systematic code in general. Okay? And that is easier for decoding, because if we receive the correct code word, we just cut the first K bits. That will be our information bits. Makes decoding a lot easier. And so that's the generation matrix. And based on the generation matrix, we can also write something as the parity check matrix. The parity check matrix has a dimension of N by N minus K. Okay? N by N minus K. And the structure of the parity check matrix is P and on top and I on the bottom. And if we perform matrix multiplication, G times H, the result will always be 0. Okay? We will always get a all 0 matrix. And for this reason, we can use the parity check matrix to check whether a code word is a valid code word. Right? So if we do C times H, where C is X times G, and G by H is 0, so we will get a 0. So for any valid code word, if you multiply it with the matrix H, we will always get a 0. Okay? So in this case, the receiver can use this property to detect if there is an error during transmission or not. Okay? So let's just look at a simple example. So let's see, this is our generation matrix, and this is our parity check matrix. Okay? If everything is fine, okay? If everything is fine, the information, if we transmit the code word and there is no error, and this is what we receive. Okay? So we can use this Y to multiply H to see if it's 0. Okay? So let's do this together. And let me see if it's possible for me to directly write on the slide. Yeah, there used to be a toolbar somewhere. Let me try this. Laser pointer. Nope. It does not allow me to use a pen. Okay. Highlighter. Last view.
You may have to enable editing first.
Where do I? Okay.
Yeah.
So
The white box at the top in the middle.
this one?
No, on the yellow toolbar.
Here. Oh, enable editing. Okay, all right. Thank you. All right, let's see if it works this time. Yeah, right. Okay, pen. So here we have y times h. So basically, here we have a y times this h matrix. So we only need to add up the rows that are corresponding to the ones, right? So because that's a row times column. So the first row times the first column, that will be, so the third element plus the fourth plus the fifth. So that's a 0, then plus a 0. So the first element is a 0 here. Okay. And similarly, for the second element, it's the first row times the second column. So we are going to have the third, the fourth, the fifth, and then the last one. So it's, again, it's a 1 plus 1 equals to 0. And the last column, so we have the third, fourth, fifth. So we have a 1 here. Then we have another 1 here. So again, it's 1 plus 1. So this is a 0 here. Okay? So if it's a valid coword, which means we do not have an error vector there, and the multiplication between y and h is always 0. So for the next example, so we still have the same coword, but the first bit is flipped. Okay? The first bit is flipped. So what we received is this new coword. And if we use this to multiply this one, so in addition to the original third, fourth, fifth, and the last row, we also need to add up the first row here. Okay? So if we add up the first row, it's going to be 101 plus 000, which is 101. So in this case, it's not 0. So we know immediately that this is not a valid coword. Okay? Any question? So first of all, as we can see here, we can use the parity check matrix to detect an error. Once we detect the error, actually we can also use this to correct the error. Okay, so that's the topic of syndrome decoding. So the received vector is c plus e. Okay, y equals to c plus e, where c is our coword and e is our error vector. Right? So because of the noise in the channel. Okay, so basically you receive some information, and then based on thresholding, as we discussed in chapter 3, we can decode those soft information and turn them into ones and zeros. And those ones and zeros, some of them will be flipped because of the effect of the noise, right? So we have, this is actually called hard decoding. So once we receive the information that is observed by the receiver is a real value number. It's our information modulated symbol plus noise, right? So that's a real number. And then we compare it with the threshold. We make a hard decision to see if this is a 1 or a 0, right? And the optimal detection we talked in chapter 3. And once we perform that hard decision, and then we use the information after hard decision to perform decoding, and this is called hard decoding. Okay, and that's what we are going to talk about in this class here. And also there is another way of doing this, which is called soft decoding. So for soft decoding, we are actually going to directly use the received information. Okay, that's going to be a real number, and we do not threshold it. We just use the real value and directly use the structure of the code to perform decoding, and that is called a soft decoding. And soft decoding has definitely a much better performance compared to hard decoding, because the reason is during hard decoding, for example, let's say if we receive a value which is 0.2 and we compare, the threshold is 0, so if it's 0.2, we make a hard decision, we make a decision in favor of 1, right? If it's, for example, minus 0.3, we make a decision for 0. So in this case, we are throwing away information. So the 0.2 and the minus 0.3 by itself, they contain useful information, right? And so those useful information can actually be used to improve the performance of the decoding. However, for hard decoding, it doesn't matter it's 0.2 or 0.3 or 0.9, we simply call them 1 in the decoding process. So we are throwing away a lot of useful information in this case. But hard decoding is simple, okay? Hard decoding is simple. Soft decoding, we need to actually, to do soft decoding, actually what we do is we calculate the likelihood of this bit being a 1 or 0, and then use the likelihood information to do decoding, right? As we can see, for example, if we receive 2 bits, one bit is 0.1 and the other bit is 0.9. Obviously, it's more likely for the second bit to be 1. And for the first bit, its value is 0.1, so it could be 0, it could be 1. It's less likely to be 1. So those information are actually quite useful. However, for hard decoding, we simply call both as 1. We make a hard decision, right? So that's the disadvantage of hard decoding. But hard decoding is a lot easier compared to soft decoding. Okay, so we are going to focus on hard decoding here. So we have C plus E, and once we make a hard decision, so these are all binaries 1 and 0s. And our syndrome is Y times H. So basically it's C plus E times H, which is C times H plus E times H. C times H is always 0. So what's remaining is E times H, okay? As I introduced at the end of last week's class, this is called the syndrome. Okay, so this is syndrome. So basically the syndrome, you can see it directly depends on the error pattern. So for each error pattern, there is a syndrome S. So we can guess the error pattern by looking at the syndrome. Okay, if this relationship is 1:1, it's a unique mapping, then our problem is solved. Okay, we don't need to worry about hard decoding or soft decoding. We just look at the syndrome, we figure out what is the error pattern, and then we can make corrections. Unfortunately, there are more error vectors than syndromes. Okay, so error vector has the same length as the code word. So there are n bits. N bits, which means there are 2 to the power of n possible combinations of error vectors. And for the syndrome vector, because y is y by n and h is n by n minus k, so the length of the syndrome vector is n by n minus k. So there are only 2 to the power of n minus k syndromes. So the number of syndromes is always less than the number of error vectors. So which means we have 2 error vectors, it's possible that they can give us exactly the same syndrome. All right? So which means, for example, you have a running nose, it could be because you catch a cold, or it could be you got a fever. Okay, so that's 2 different things, but it might give you the same syndrome. So just by looking at the syndrome, we might not be able to uniquely identify what is the error pattern. Okay, so some error vectors might have the same syndrome, and given syndrome, there might be more error vectors. So for syndrome decoding, it's easy, we just randomly pick one, okay? And the rule is essentially we pick the one with the least number of ones, okay? So because in general, it's unlikely that all the bits are in error, right? Most likely, we have just 1 or 2 bits are flipped. So we just pick the one with less errors. And so that's how syndrome decoding is performed. So we look at the syndrome, and we pick the one with less number of less errors. Okay, so just a simple example. So we have the generation matrix here. We have the generation matrix here, and once we have the generation matrix, we can write a parity check matrix. Okay, so this is a 5-2 code. And that's the identity matrix and the parity submatrix, right? And based on this, we can write our parity check matrix. If you recall, it's PI, right? So basically, we are going to have 101, 011, and the I is going to be, to be precise, it's an I of size n minus k. How do I erase this thing? Is there a tool? Eraser, okay? So, pen, n minus k, okay? N minus k in this case is 3. So this is our parity check matrix. So in this particular case, we have 2 bits of information. They are mapped to 5 bits of code word. So the total number of error vectors will be 2 to the power of n. Okay, our error vector is always has the same length as the code word. So that's 5. 2 to the 5 is 32. Okay, and the number of syndromes is 2 to the power of n minus k. So we have 32 possible error vectors, but we only have 8 syndromes. Okay. Question? So in this case, we have 4 valid code words, and there are totally 32 possible combinations, and this is 4 out of these 32. Okay, this is 4 out of 32. So let's just do a quick calculation of the syndromes of different error vectors. So again, let me write down H here. So H is 101,011. So this is our H matrix, priority check matrix. Let's figure out what are the syndromes. So if it's an all zero vector, our syndrome is always 0. And if the first bit is flipped, it's just going to be the last row of the priority check matrix. So it's 001. And if the second bit is flipped, it's going to be this row here, 010. And the third bit, and the fourth bit, which is going to be this row here, 011. And this bit is flipped, it's 101. Right? So we can just keep going for different possible errors. So this, from 2 to 6, these 5 vectors, these are all possible error vectors with 1 bit of error. So we exhaustively listed all of them. Right? And then after 1 bit of error, we might have 2 bits of error. So 10001, so which is this row plus this row here, is going to be 100, right? Because that's a 1 plus 1 is 0 here. And then the first bit or the next and the second to last bit, so that's going to be this row, the first row plus the fourth row here, it will be a 111. Okay, it will be a 111. So the next one, 10100, it's going to be the first row and the third row. That's going to be 001 here, right? So we have 1, 1, 0, 0, and 1 here. And the last one here, the first row plus the second row, it will be 1, 1, 0. If we look at these syndrome vectors, and actually we can see, as we know, there are a total of 8 syndrome vectors, and here we listed 10 of them. Some of them have to be the same. For example, these 2 are the same, so which means these 2 error vectors, these 2 error vectors have the same syndrome. And as I said, we simply just pick the one with the least number of errors. So in this case, usually we just pick this one as our error vector because this is more likely. Okay, the probability of having 1 bit of error is actually bigger than the probability of having 2 bits of error, right? So for example, if the error probability is PE, and if all the bit errors are independent, which is true in AWGN channel, then the probability that 2 bits are in error is going to be PE squared, and the probability that 1 bit in error is PE. And PE is always less than 1, so PE is always greater than PE squared. It's always more likely to have just 1 bit of error compared to 2 bits of error. And the same thing, right? If we have 3 or 4 or 5 bits of error, because the PE. Okay. Anyway, so these 2 are the same, and there should be another one. And which one is that? 110, 001. Yeah, this one here. Thank you. These two are the same. Okay, and again, we can simply just pick the second one. So if we simply pick, we can pick all the 1 bit of errors. Okay, so we can keep all these ones. So when we see the syndrome, and we will just map them back to the error, and then we can make corrections. Okay, and in the meantime, we can correct this one here and this one here, right? We can also correct these two. If it's 111, we can say that it corresponds to these 2 bits of error. And this 11 could also be generated by some other patterns, but we simply just pick this one because there is no 1-bit pattern will give us a 11, and that's the 2-bit pattern, right? So we can just pick this 2-bit error pattern. So for this code, particular code, it can correct all 1-bit errors. If there is just 1 bit of error, this code can correct all of them. Okay, and it can correct some of the 2-bit errors, but not all of them. And it can do nothing about 3 bits of errors. If there are 3 bits of error, and even if we make a detection based on the syndrome, the decision will be wrong. Right? The decision will be wrong because, and also for example, if our actual error vector is this one, we got a syndrome of 001, and based on our rule, we pick this error vector. So which means our decision is wrong. But by choosing the least number of errors, we can minimize the error probability. Right? Error is inevitable, but we need to design a rule that can make the error less likely. All right, so that's just a very simple example of syndrome decoding. Question? Okay. So for syndrome decoding, usually what we do is we write a syndrome table, and then when we implement our code or design our system, we just compare the syndrome table and figure out what is the errors. Okay, so that's exactly what we did in the previous slide. The syndrome 0 corresponding to the 0 vector. 001 corresponds to this vector here, even though in the previous slide 001 could also correspond to the 2 bits of error, but we give priority to 1 bit of error here. Okay, so basically we have the syndrome here and we have an error vector here, and it's a 1-to-1 mapping, and given a syndrome we just pick an error vector. Okay, the syndrome has to be one of these 8 possibilities. Right? We will always get these 8 possibilities, so we will get an error. So you can correct all 1-bit errors. It can detect 2 bits of errors, right? And more than 2 bits of errors is beyond the capability of the 5.2 code. Okay? Later on, we are going to discuss what is the detection and correction capability of a particular code. Okay? And there are actually theories behind that. So for this simple 5.2 code, it can correct all 1-bit error and detect 2 bits of errors. Okay? And for this 5.2 code, for every 2 bits of information, we add 3 bits of redundancy, right? And the total covert length is 5. Okay, and also there's something called the standard array. And the standard array is a table, and the column of the table are all the 2K code words, and the rows are all 2n minus k correctable error patterns. Okay, so that's called a standard array. So for the column, it's all 2k code words, and on the rows is all 2n minus k correctable error patterns. So let's just look at a simple example of this standard array of this 5.2 code. It's also a tool. Standard array is a tool used for the analysis of a linear block code. Okay, so our G is and our H is okay, still the same code. And now let's write down the standard array. So the standard array is columns including all the 2k code words. So here our k equals to 2 and our n equals to 5. So which means we will have 4 columns. And the 4 columns including all the valid code words, okay? And the length of each code word is 5. So, for example, if our information is 00, the corresponding code word will be, so that's our code word, right? And if our information is 01, the code word will be, if it's 10, the code word will be, and finally, if the information bits are 11, so it's the summation of these two rows. So these are the 4 possible code words corresponding to the 4 different combinations of information. Okay, any question? So the code word, again, as I said, is always a linear combination of the rows of the generation matrix. And each row of the generation matrix is also a valid code word. And 0 has to be a code word. Okay? And they form a field. They form a field. Okay? And for a field, it's closed in linear operations, so which means the summation of any 2 code words is always also a code word. Okay? And just as a simple example, for example, the 3rd and the 4th code word, if we add them up together, you will find that's going to be exactly the 2nd code word. Okay? For example, 1 plus 1 will be 0, 0 plus 1 will be 1, 1 plus 1 will be 0 again, 0 plus 1 is 1, and 1 plus 0 is 1. So the 3rd code word plus the 4th code word is, again, code word. Okay? That's the property of linear block code. The combination of any 2 code words is always a code word. Okay? So that's the columns. And the rows are all the possible error patterns. Okay? So the rows are all the correctable error patterns. So for the correctable error patterns, we have all the 1-bit errors. We have all the 1-bit errors. Okay, and actually I should have written, let's see if I can move this down a little bit. Okay, that's fine. So I'm just gonna, so that's the first one, huh? There's no error. And all the 1-bit of errors, and also, so these are all the 1-bit of errors, and also we have a couple of 2-bit errors. Okay, so a couple of 2-bit of errors. And what we do is for the valid code word, and then we add them back to the error vector. So for the first row, it's simple. It's still just simply the code word themselves, because there is no error. And for the second row, we add the code word with the error pattern. Okay, so that's the second row. And we can keep going. And for the third row, we add the error pattern to the code word. So that's going to be a 0 here. So the 4th bit is flipped. Okay, and we can keep going. We can keep going, and we can populate this entire table. And this table is called the standard array. It's pretty simple. Okay? It's just a code word plus the possible error patterns. And once we write the standard array, so we have a name for the elements here. Each row here is called a coset. Okay, it's called a coset. And the first element is called the coset leader. So basically the error vectors is called a coset leader. And all elements in the same coset, they have the same syndrome. Right? Because all elements in the same coset, they have exactly the same error pattern. And therefore, they have exactly the same syndrome. Okay? So that's the concept of standard array. And the idea of standard array is also, by looking at the elements, we look at the table, and we can directly figure out what is the correct code word and what is the information. For example, if our received information is 10111, just by looking for 10111 in this table, and we will find out that it's the possible error pattern is here, and our correct error vector is here. So in this case, we don't need to do any multiplication or anything. We can just use a table to figure out what is the transmitted information. Okay? So this is our valid code word, and our correct information is 10. Okay? And the size of the table is basically we have 2 to the power of k columns, and we have 2 to the power of n minus k rows. So the total number of elements in the table is 2 to the power of n. So which are all possibilities of the received code word? We are receiving an n-bit sequence. There are a total of 2 to the power of n possibilities, right? So whatever you receive, it will be an element in this table. And once you find out that element in the table, and you can directly find out what are the correct information. Okay? So this makes the decoding even more straightforward. We don't need to do any calculation. Just find the elements. Okay? So this is called a standard array. Okay? So now let's look at an example. So let's see. We have a 5-2 systematic code, and again, it's the same code. And we have an error vector. And let's find out, let's perform the decoding process. Okay? This is encoding, given information, what is the code word, and what is the received information. From the received information, how do we derive what are the transmitted information. Okay? And again, let's do this. 1. So that's our G, that's our H. Okay, so for the first question, let's assume our information is 01, and in this case, our C is X times G, and which will give us the second row of G. So that's our code word. And our received information is, because of the effect of noise, some of the bits are flipped. So we assume in this example, it's the third bit is flipped. So we receive. Okay, so the third bit is flipped. So that's Y. And at the receiver, so when we receive the information, if we do not use standard array, the first thing we do is we do Y times H. If we do Y times H, so that's going to be the summation of the last 4 rows here. We will have 1, O, O. So this is our syndrome, okay? 1, O, and O, okay? So that's S. And given S, and we need to look at the syndrome table. So that's 100. 100 is here. It corresponds to the error vector of 100. Based on the syndrome table, we figure out what is the error vector. And once we have the error vector, so the detected code word will be Y plus E, right? Or Y minus E. And in the binary domain, it's the same. So Y plus E will be 01, 0, 1, 1. Okay, so the third bit is in error. And once we have the C, we know it's a systematic code. So X will simply be the first 2 bits of the systematic code. So our X is 01 in this case. So in this particular example, because we have just a 1 bit of error, and based on syndrome decoding, we can perfectly recover the original information without any error, even though one of the bits are in error. Okay, so that's the first example. Question?
I have a question.
Yes.
The YH part, like a 100, and how do you get that error is, I mean, my bad, is the Y. How do you get like 0, 1, 1, 1, 1 when you plug?
Here? Okay, so it's Y is C plus E, and here I assume that the error pattern is 0010. So I add them up together. That's how I got it.
And how about the next step as well?
The next step, I simply use Y times H. So this vector times the H matrix. And basically it tells us that's the summation of the last 4 rows. So O plus 1 plus O plus O is 1 here. 1 plus O plus 1 plus O is O here. 1 plus O plus O plus 1 is O here.
Got it. Thank you.
All right. So that's the decoding procedure. In the next example, so let's assume that we transmit 1, 1. We follow exactly the same procedure. So X is 1, 1 in this case. So the code word will be the summation of these 2 rows, and which is 1, 1, 1. So 1, 0. Okay. So this is the code word, and our received information is X plus actually that's X, and this is C. Okay. So the received information is C plus E, which is 11110 plus. And in this example, we assume that we have 2 bits of error, 10010. So our received information will be 01100. Okay, 2 bits are flipped, the first bit and the 4th bit. So that's our Y, and then we perform syndrome is Y times H. Okay, is Y times H. And our Y is here, and our H is this matrix here, and this tells us it's simply the summation of the 2nd row and the 3rd row. So our syndrome is here. And based on the syndrome table, let's figure out what is the error vector. So the estimated error vector, based on syndrome table, is 10010. It's 10010. Okay. And finally, our estimated code word is simply Y plus the error vector, which will be 11110, and our estimated information vector is simply just the first 2 bits, which is 1, 1. So again, we can correctly recover the information. So our detected error vector is exactly the same as the actual error vector. And the reason is this error vector is in the syndrome table, right? If this error vector is not in the syndrome table, the detected error vector will be different from the actual error vector. We are going to make an error in the detection, okay? But in this particular example, 10010 is in the syndrome table, so we can correct it. So if the error vector is in the syndrome table, we will be able to correct it. If it's not in the syndrome table, we are out of luck. We are going to make an erroneous detection. Okay. So that's example number 2. So example number 3. So let's look at a couple of more examples. Okay. Example number 3. So we still transmit 01, but in this case, our error vector is 00110. Okay. So again, I need to write down the matrix. So that's our G and H matrix. For example number 3, X again is 0, 1. So C is, that's the same as example number 1. We have the same code word. And our received information is C plus E, 01011. And our error vector is 00110. So the summation of these two will be 01, 1, 0, 1. Right? So we have the second bit is 1, the third bit is 1, the fourth bit is 0. Yeah, right. So that's our Y. And in this case, if we do Y by H, so there will be the summation of the second, third, and the last row here. So the second, the third, and the last row, we add them up together. So our syndrome is 110. And our syndrome is 110 means our estimated error vector, we need to go back to the syndrome table, 110. So it's going to be 11000. Okay, so our X hat will be Y plus E hat. Y plus E hat, it will be 10101. Okay, the first two bits are flipped. That's the code word C. And our X hat in this case will be 10. And the actual X is 01. So we make an error. So I'm here using this example to show that with the syndrome decoding, very well we could make errors. Okay, we could make errors. It's not perfect. So in this case, we have 2 bits of error. And the reason that we make this error is because the actual error pattern is not in the syndrome table. And unfortunately, this error pattern and this error pattern, they have exactly the same syndrome. Okay? They have exactly the same syndrome. Okay? So if you look at the syndrome table, so we have this pattern in the syndrome table, but 00110 is not here. Okay? It's not here. So we made an error. Okay? So the last example. Assume X is 1, 1. So our C is 11110. That's the same as the previous example. And Y equals to C plus E. And again, it's the error vector is different. And our error vector here is 10010. So the first and the fourth bits are flipped. The first and the fourth bits are flipped. So once we get this Y, so S equals to YH. So it's the summation of the second and the third row here, the second and the third row here, which will be 111. And based on our syndrome table, 111 corresponds to 10010. Uh-huh.
I think I learned that you direct is wrong.
So you mean, oh, okay. I copied another. So this is 001. Okay. Yeah, thank you. So that's 1 bit of error. So which means we should be able to correct it. Okay, it can correct all 1 bits of error. So 111, it's just everything add up together. It's going to be 001. So the syndrome is 001. If it's 001, let's go to the syndrome table. 01 is 0001. Okay. And this is our estimated error vector, which happens to be exactly the same as the true error vector. So C hat will be y plus E hat, which will be 11110, and our X hat will be 11. And again, this is a successful decoding. Okay? So we looked at 4 different examples, and if it's 1 bit error, and it's guaranteed that we will be able to correct it. Okay? And if it's 2 bits of error, for some of them we can correct it, for some others we cannot. And for 3 bits of error, they are out of luck. Right? So that's just a syndrome decoding, very simple. Okay? Nothing fancy here. Okay? And we looked at the 5.2 code, and we can see it can correct 1 bit of error, and it can detect 2 bits of errors. So now let's generalize this. Let's look at the error detection and error correction capability of general linear block code. Okay? So basically, the design of the linear block code. So what kind of code is a good code? So how do we quantify if a code is good or not? Because here we have k bits of information, so we have 2 k possible combinations, so which means we only need 2 to the power of k code words. In the previous example, our k equals to 2, so we only need 4 possible code words. However, the length of the code word is 5, so there are 2 to the power of 5, or 2 to the power of n possible combinations. And in the previous example, we have 32 possible combinations. Okay? We have 32 candidates, and from these 32 candidates, we only need to pick 4 of them as our code word, and the others are invalid. So the question of the code design is actually how to best pick the best 4 combination out of these 32 possibilities such that we can minimize the error probability. Right? So that's our probability. So the question is, how do we make this choice? Right? And let's just look at a very, very simple example that might give you some hint about how to design this code. So let's see, we have a 3-1 linear block code. And 3-1 linear block code means we have 1 bit of information mapped to a code word of length 3, right? So 1 bit of information, we have just 2 possible combinations, right? And we have 8 possible code words, right? From 0001 all the way to 11. So we can pick. So one way is just we randomly pick 2, right? For example, we can pick 000 and 111. So this is our repetition code, right? And another possible choice is we use 001 to represent 0, and we use 110 to represent 1. Okay? So that's another code. So basically, by picking 2 code words out of these 8 possible combinations, you will have a new linear block code. So how many code that we have in this case is 8 choose 2, right? 8 choose 2. So that's the total number of code that we can have, and particularly for 8 choose 2 is pretty easy to calculate. So we have 28 possible combinations. So we can design 28 possible codes. So which one is the best? So that's the question, right? And another way of doing that is we use 0011 to represent 0 and 010 to represent 1. And you can keep going, and I can list 28 different codes. So we are only interested in the best one, okay? And for the rest, because they have the same code rate, and in reality, we only use the best one. So how do we quantify the performance of the different code? And one easy way to do this quantification is using something called the Hamming distance, okay? The Hamming distance. The Hamming distance is actually a very simple concept. The Hamming distance just tells us the number of bits that are different between these two code words. Okay? So for example, for the first code, we have 3 bits, and all 3 bits are different. So we see the Hamming distance between these two code words is 3. And for the second code word 1 is 001, and code word 2 is 110. And again, so the first bit is different, the second bit is different, the third bit is different. So the Hamming distance is, again, 3. And actually, we can prove that these two codes, they have exactly the same performance. Right? So the repetition code or the code here, they are exactly the same, essentially. Okay? They're exactly the same. And I mean, in terms of performance, of course, the code words are different in terms of performance. And for the third one, the first bit, they are the same. The second bit are the same. The third bit, they are different. So the Hamming distance between these two code words is just 1. Okay? It's just 1. So why do we want the Hamming distance to be big? So in this case, the largest possible Hamming distance is 3, right? Because the code word is 3. The worst case, the best case scenario is every bit is different. Okay? So our Hamming distance is 3. So the reason for that is because, again, as I mentioned earlier, the probability that all 3 bits are flipped is very, very small. Okay? But the probability that just 1 bit is flipped is quite high. Okay? So for that reason, most of the errors, they won't flip all the bits. So we would like the two code words that are as different as possible. Okay? Basically, you want to design two code words at the receiver. From these two code words, you would like to figure out what are the original information. And for this reason, you would like these two code words to be as different as possible. And if they are quite different, then there is a less probability for you to confuse one code word with another one. Right? If there's no confusion, you can always make the correct decision. Right? So the Hamming distance is a measure about how different these two code words are. Okay? As a simple example, let's see if somehow the noise is very strong during the third bit, so the third bit is flipped. If the third bit is flipped, and the receiver, we transmit a 00, we receive a 001, we will still be able to detect it's a 0, right? And however, if we use this code, at the transmitter, we transmit a 011, however, at the receiver, we receive a 010, and we will make a decision of 1. So we are going to make an error. So for the same amount of bit errors, a code with a smaller Hamming distance is more likely to make an error decision. Okay? And a code word with bigger Hamming distance, and it's less likely for us to confuse between them. So basically, we would like the code word to be as different as possible. So that's the general rule for the design of code. And this is not just for linear block code, for any code, for channel code in general, right? So we have a group of information, we mapped it to different code words, and we would like this code word to be as different as possible. Okay? If they are quite different, then we will be able to make correct decision. So rule of thumb here is we want the code word to be as different as possible. And so for the repetition code, we have 3 bits of difference, and for this one, we have 1 bit of difference. Okay? Hamming distance is between two binary code words is defined as the number of bits in which they differ. Okay? Larger Hamming distance means two code words are further apart, then the probability of choosing the wrong code word is smaller, and it will give us a better power efficiency. A smaller error probability means we can operate under a lower signal-to-noise ratio, right? Better power efficiency. So in the previous example, what we saw, we only have 2 code words. So the Hamming distance is simple, just the distance between these 2 code words. And in reality, our k in general is greater than 1. So we have more than 2 code words. In the previous example, we have 5 2 codes. So we have a total of 4 code words. So for each pair of code word, we will have a Hamming distance. So how do we characterize the performance of those kind of code? We use something called the minimum Hamming distance. Okay? So for any 2 pair of code word, we can get a Hamming distance. Okay? And then we can get several Hamming distances. And we find the smallest one. That is the performance limiting factor for that particular code. Okay. If there are more than 2 code words, 1 Hamming distance for each pair of code word. Okay, so that's the ith code word and the jth code word. We can find out their Hamming distance, and we find out the minimum of all those Hamming distances. Okay, so let's look at the 5.2 code. Let's go back. So yeah, that's the code word here. Okay, that's the code word here. So let's find the Hamming distance. Okay, so I still have the pen. So for the, let's see, we totally have 4 code word. And out of 4 code word, how many pairs will we have? Pen. So for pick 2, so we have 6 possible different Hamming distances. So let's list them one by one. D, 1, 2. So the first one and the second one, the Hamming distance is 3. The first 2 code words, they differ in 3 bits, right? And the first one and the third one, again, they differ in 3 bits. The first one and the last one, they differ in 4 bits. Okay. And then the first one and the third one. We already got the first one and the second one, so the second one and the third one, the second one and the third one, they differ in 1, 2, 3, 4. They differ in 4 bits. Okay, and the second and the fourth one, so they differ in the first bit, the third bit, and the last bit. And finally, the third one and the fourth one. For the third one and the fourth one, we have 1, 2, and 3. That's all the possible combinations. We have 6 pairs, right? We have exactly 6 pairs. And obviously, the minimum Hamming distance is 3. All right? The minimum Hamming distance is 3. Any question? Okay. And actually, there is an easier way. Yeah, question?
The ones with the Hamming distance of 4, are those the ones that can be corrected if there's 2 bits in error?
No, this does not necessarily correlated to that it can be corrected. Okay, that does not mean that. Any other question? And actually, so here I listed all the possibilities. Actually, there is an easier way to find the minimum Hamming distance, which is we just use the 0 code word compare. Actually, this 3 is enough. We just compare the Hamming distance between the 0 code word and all the other code word. Okay, and we can actually prove this because 0 code word and geometric speaking, we can represent each of them as a point, and the 0 code word, geometric speaking, is equivalent to any other code word. So we just compare the 0 code word with all the other possible code word, and what is the smallest distance, which means the distance between the 0 code word and any other code word is actually the weight of the code word itself. The weight means the number of non-zero elements, right? So here it's 3, 3, and 4, right? So the distance are 3, 3, and 4. So the minimum Hamming distance is actually the minimum weight of the non-zero code word. Okay? Any question? So that's the concept of minimum Hamming distance. Okay? So for LBC code with minimum Hamming distance dmin, So all error patterns with error bits less than or equal to dmin minus 1 can be detected. Okay? And all error patterns with error bits less than or equal to dmin minus 1 divided by 2 can be corrected. Okay? So before I explain why, let's first look at the previous example. In the previous example, our dmin is 3, so it can detect all 2 bits of errors. And if we plug in 3 here, 3 minus 1 is 2, 2 divided by 2 is 1. And this is the floor operation, which means if it's 1.2, it's going to be a 1. Okay? So it's the largest integer that is smaller than this value. Okay? Again, if this value is 1.9, the floor of 1.9 is still just 1. Okay? It just take the integer part. So dmin minus 1 divided by 2, in our example, dmin minus 1 plus 2 is 1, so it can correct 1 bit of error. It can detect all 2 bits of errors. Okay? So why is this the case? Why is this the case? So let's see, we have 2 code words. I'm just going to represent them as a point. Okay? So let's see, we have C1 and C2. So the Hamming distance between these 2 code words is 3. Okay? Is 3. So let's see if we have, so let's see, if we flip 1 bit, we will get a code word here. And if we flip a second bit, we will get another code word, which is not a valid code word, of course. Okay? And if we flip a third bit, we will get a C2. Okay? So, which means, if in case 3 bits are flipped, it's possible that we will get another code word, because the minimum Hamming distance is 3. So we transmit 1 code word, and we flip 3 bits, and it's possible that it will give us another valid code word. Okay? And in this case, we won't be able to detect the 3 bits of error. It does not mean that we cannot detect any 3 bit of error. It means that we cannot detect some 3 bit of error. Okay? Because the minimum Hamming distance is 3, so if we flip 3 bits, it's possible that we will get a valid code word. Okay? And as an example, so if I come back here, so let's see if we transmit a 00000, and if the second, the fourth, and the fifth bits are in error, I flip that 3 bits, and then I'm going to get another valid code word. If I do syndrome decoding, the syndrome will be all 0, so I won't be able to detect that. Right? So however, if I flip 2 bits, because for any pair of code words, they differ at least in 3 bits. If I flip in 2 bits, it will never become another code word. Okay, so which means if I flip 2 bits, I will always end up at here, and in that case, the syndrome is always non-zero. Okay, so that's why if the minimum distance, Hamming distance is dmin, then I can detect any dmin minus 1 bits of errors. Okay, because if I have only dmin minus 1 bit of errors, I will never get to another valid code word, and the syndrome will always be non-zero. So I can always detect that errors. Okay, so for our 5.2 code, in that case, which means as long as it's 2 bits of error, we can always detect that. But for 3 bits of error, sometimes we can detect it, sometimes we cannot. Okay, so that's the error detection capability. And for the error correction capability, again, it's easy to understand. So we need to flip the bit 3 different bits to arrive at a different code word. So we can draw a line between the 2 code words, right? So if we have just 1 bit in error, so let's see we transmitted CY. And if 1 bit in error, we end up at here. And then we can compare the Hamming distance between the received code word and the possible code word. And obviously this one has a shorter distance than this one. So we make a decision in favor of CY. Right? So in this case, we can correct 1 bit of error, because for 1 bit of error, if it's just 1 bit of error, it's guaranteed that the received information has a shorter distance to the true code word than the Hamming distance with any other code word, because the distance between 2 code words is at least 3. Right? If we have just 1 bit of error, and the received bit will always have a distance at least 2 or larger. Right? So the Hamming distance here is 1, and the Hamming distance here is 2. And we can always make the correct detection. Okay? But if it's 2 bits of error, then it might be closer to another code word, right? So in that case, we don't know. In that case, we don't know. Okay? So that's the reason. So this point is actually d mean minus 2, right? So that's 1.5. And then we can only have integer number of errors. That's why we put the floor there, right? That's why we put the floor there. So that's a very easy explanation. So the error detection capability is d mean minus 1, and the error correction capability is d mean divided by 2. And then take the integer part. Okay? Any question? And that's a very useful result because this is in general true, not just for linear block code. And this result is actually true for any channel code. It doesn't matter, it's convolutional code, it's linear block code, it's turbo code, and we always have this result. So the d mean for a binary code is the performance limiting factor of this code. So when we want to design code, again, it doesn't matter if it's a linear block code or convolutional code, we always want to maximize the minimum Hamming distance. Okay? This is called a max-min problem. We find the minimum Hamming distance, which is the worst case scenario, and we would like to maximize the worst case scenario. Okay? And this kind of design metric is used quite commonly in engineering designs. This is called a max-min problem. Okay? We cannot max all of them. So we just pick the worst case scenario. We maximize the worst case scenario. Okay? Any question?
You said the cycle of this d mean by 2, but in slide it's written d mean minus 1 by 2.
Oh, okay. Yeah, right. So it should be d mean minus 1. Okay. So there are just in the case that let me see, 1.5 d mean minus 1. Yeah, right. So in this, so here I have a 3. If I have 1, 2, if we use 4, probably it's easier to see that. So let's see. If I use an odd number of d mean, actually it's not that obvious. So I made a mistake here. It should be d mean minus 1 divided by 2. If the Hamming distance is 4, if it's 4, so in that case, if I use d mean divided by 2, it will be 2. And these 2 bits actually is right on the line here. And when it's right on the line, we can tell if it's, let's see, if there are 2 bits of error flipped, so we cannot tell whether it's from C1 or from C2, so we cannot differentiate in this case. So we have to get rid of the middle point, and that's the reason we have the minus 1 there. Okay, and yeah, that's a good point there. The what?
You say the different margin?
The different margin?
So the dotted line.
Yeah, right. So in this case, we should just set the margin here, right? So because the middle point, it doesn't count. And for the middle point, we cannot detect it, right? So it should be d mean minus 1 divided by 2 here, right? Any other question?
Why do you use LPC?
So what are the typical values that we use for
In which communication systems we use?
There are lots of communication systems use LPC codes. For example, as I mentioned earlier, the cable TV system, our digital TV, is using the linear block code, and it's using a special type of linear block code which is called the Reed-Solomon code. And Reed-Solomon code. Okay. And it's used in the cable TV system. And actually, I was talking to a professor from University of Southern California. That was 2 years ago when I went to attend a conference, and that professor, he has just retired, and he told me some story about Dr. Solomon. And actually, when he first became, the professor is a Chinese professor, and when he first joined the USC, that was like 30, 40 years ago, And at that time, his English was not good. And his theory, his research was top-notch at the top of the world, but his English was not that good. So the University of Southern California asked him, so probably you should find an English tutor to improve your English first. So he found an English tutor, and guess who is the English tutor? It's Dr. Solomon. And he has retired for a while at that time, and he was just, he loves to teach English, and he loves music. So he has a special form of teaching English, and he asked the person to sing in English, and that will help the English pronunciation. And at that time, I did not know exactly how he found this English tutor. Probably it's just by accident or by chance, because at that time he didn't know Dr. Solomon was actually the guy who invented the Reed-Solomon code, the linear block code there. And then after he went there and he realized this is the Dr. Solomon who invented the Reed-Solomon code. And so then he learned English from him, of course, and the professor from USC, he is also an information theorist. He also works on coding. And then he asked Dr. Solomon, and he realized, at that time Dr. Solomon has retired already for a number of years. He asked him, they were discussing some information theory problem, and then he realized that Dr. Solomon was not even an IEEE fellow. And he made such a big contribution to the field. And then this Chinese professor, and he called his advisor, and he told him, I'm working with Dr. Solomon, and he's not even an IEEE fellow. And then they started to nominate him for the IEEE fellow. And then the second year, and with his credential, of course, there's no problem. He got the IEEE fellow. And then the year after that, he passed away. So that was like 20, 30 years ago at least. So I was having lunch with this professor, and he told me this entire story. It's pretty interesting. And at that time, there was also a movie star from China. She's a lady, and also she was learning English from the same person, from Dr. Solomon at that time. Okay, anyway, so that's just some side story. And when you guys asked about that, I know I suddenly it came back to my mind. Anyway, that's just some interesting story. And Reed-Solomon code is a very widely used code, and also for our CD, it's also used in our CD. Okay, so for our CD, because what we have is digital music, it's ones and zeros, right? And for the CD, you can imagine if you have some dirt or if you have some smudges, you use finger to touch the surface, it might flip the ones and the zeros. Okay, and that's like noise. And so, but when you play it back, and you can hear the perfect music, and you can load the software, and it's because of the channel coding that is on the CD, and that's the same code there. That's also linear block code. Okay, and actually for the coding community, there is a huge amount of efforts devoted to the coding of storage media. Okay, and just like, and another example is your hard drive. So for the hard drive, when you write a file there, one and zeros, it does not directly write the ones and zeros there, because the hardware medium is magnetic. The magnetic is prone to the interference, and also the bits in the magnetic medium could flip. And those information are encoded first and then stored in the media. Okay? And that's another example of channel coding. So it's not just for communication. You might not know it. It's everywhere. Okay, so anyway, so that's all that I have today. Any other question? All right, so hope you guys have a nice Thanksgiving, and we'll see you next week. Yeah, I got it. And
You got to get the hard copy?
oh no, I already got the soft copy and I've already got everything. So it's gonna be graded. And yeah, I didn't bring it back yet.
Okay. Do you got all the tests from the electric 1 to 4? Because we counted, we have about
There's
52.
one. There is one more.
There is 59 students and we counted 52.
I don't know the rest, right? And there will be one more. So you got the Fort Smith ones, right?
Yeah, I'm
And,
counting all of them.
Yeah, right. And then there are 2 from the CE testing center, and then the rest are just in class. So probably some students drop off.
Because that's many. I mean,
Yeah,
there's
right.
69 students.
You have only 52 in total.
52 in total.
Yeah, so it's possible. So okay. Yeah, I have one more. So why don't you come up with me, and I'm gonna give you that one. And also, were you grading the quiz? Or did you give it back to me? Quiz number 2? Do you know? Oh, you have. Did you give it back to me? Not yet. Okay. I have some quiz from Fort Smith, which I didn't give that to you yet.
It should be.
Yeah, they are in my office. So yeah, just come up with me and then let's pick them up.
I submitted the project 4 a bit late.
Okay.
It's not here.
Yeah, it's not finished grading yet.
It's just like, it says not theoretical term, but it's here.
Okay. So is there, and that's 3. Oh, so you just plot 2 different
Yes, it's
figures.
just that
Okay.
it had, like,
I see.
I was
Okay.
following the.
All right. So yeah, why don't you send me an email and I will correct that. Okay. Yeah. Okay. All right. Okay.
So designing programs is basically about linear algebra.
Yeah, it's mainly about algebra, and sometimes it's nonlinear, and sometimes it's linear, and it's not the matrix operation that we talked about. That kind of algebra. It's actually very, very tensile algebra, and it's using the subspace and all those.
Still,
those
some
kind.
people are still working on designing.
Yes, still there are. If you go to the Information Theory Conference, ISIT, there are a ton of tracks working on the code designs. And recently there is another type of code which is called polar code, and it receives lots of attention. So there are lots of papers on those codes. Okay.
Just I understand why